Hello everyone, welcome back to our reading group. We're picking up right where we left off in the middle of section 2.2, looking at examples of limits and colimits. So far we've talked about things like products and coproducts and kernels and co-kernels and exactness. And the sort of interesting thing about what we've done so far is that we've found a fair bit of variety of examples that can be built out of things that are basically limits of diagrams that have just two objects, or at least in the case of things like products and coproducts, have as their prototypical examples things that have only two objects. And now we want to go a little further, and we want to think about some more complicated categories. So what we're going to do today is begin by looking at objects with three categories, three objects and two non-identity morphisms. And then we'll explain how, in a sense, this allows us to think about essentially everything. And hopefully we'll see some interesting examples of that either this time or next time, depending on how long it takes. So our prototypical three-object category will look like this. And again, we're not going to draw the non-identity morphisms. And we take our functor alpha out of this into some other category, which will give us a diagram that looks like this. Oop, the arrow goes the wrong way. Force of habit. And we'll start by looking at just what we can get by taking limits of these types of diagrams. If I take the inductive limit, then this gives us what's called the fibered coproduct, which is usually written like so, like the fibered product with the sort of disjoint union symbol, except we put this little x there to indicate that it's sort of fibered over x. And I'll say what that means in a little bit, just sort of bear with me. You want to think of these as sort of similar to ordinary coproducts, except somehow remembering the data of x and the morphisms out of it. In order to make a limit, we're going to need some compatibility conditions that we'll have in the larger diagram. Because remember, for ordinary coproducts, when I took the limit, I just had stuff like this. I had y0 and y1 both pointing into a common thing, and this was the limit. Now I have this other object, x, mapping over them, and maybe this is better drawn than as a box. This is at least more common. Come on, let me scroll. And so we need to think about how this changes things. In the category of sets, pretty much always the best place to start, we know that the coproduct is just the disjoint union. And so now, if I'm interested in this sort of fibered coproduct, then I know that whatever I'm going to construct, well, it has to resemble the disjoint union, but it also has to know things about the maps from x to y0 and y1. And in particular, if this diagram is going to commute, then if I pick any x in x, then wherever it goes, maybe I label these guys f and g, and then we call these guys I and j, just borrowing the notation from the inclusion maps. Then I know that if I do f of x followed by I, and I can also do j and g of x, these need to be equal to each other. And so this is sort of imposing restrictions coming from the maps. And that's how you should think about this. Or if you like, maybe we're gluing these things together, y0 and y1, instead of just having a disjoint union, insisting that whatever is in the image of f and g, we make those things agree. And this is not a pointless example or a pointless analogy. In fact, if I insist that these maps are, say, continuous, and I'm thinking about topological spaces, then if all I have to do is just give this fibered coproduct the quotient topology, and this exact argument tells me not only what the intuition is, but it tells me exactly what the fiber coproduct is. These are the so-called adjunction spaces. If you're familiar. Sort of what's happening is I'm taking two spaces and I'm gluing them along their common image. So like, let's say, for example, I take a surface. Here's a surface, and here's another surface. And then I take, let's say, I don't know, a disk. And I'm going to map this into here. And I'm going to get that disk in particular. And then I'm going to do the same thing over here. Then what I want then, the limit object, will have to be something that resembles the disjoint union. So I start with something that looks like this, but now the red and the green have to be identified. Maybe I make it purple then. And these need to be glued together with a common disk between them, making a genus 3 surface. Okay, with that said, let's take a look at what happens in some algebraic settings where the idea is somehow similar, but sometimes you have to have a little bit of care because, you know, algebraic objects can be sort of wonky. For vector spaces, it's if I take, like, I have linear maps, x to y0 and x to y1. Well, I can take a basis for x, and if I can look at the image of these maps, I don't know what to call them, maybe I call them T0 and T1. I can take a basis for their image, and then it's not so bad to explain what's going on, because in that setting, all I have to do is complete their images to a common basis, and then just identify those images. So this is sort of similar to the set theory situation, except instead of dealing with the whole vector space, I can just limit myself to dealing with bases, and I sort of reduced myself to the set theoretic situation because linear maps are sort of defined to be free over a basis. Maybe that doesn't mean anything to some of you guys, but hopefully to at least a few of you, then that checks out and tells you how to construct it. Let's think about what happens in the world of groups, because that's both a little bit less trivial, and also it fashions us with, how do I say, a relationship to the example I just gave. So what is the coproduct of groups? Well, this is a notion called the free product. And the easiest way to describe it is if you know about generators and relations. So if I have a presentation for my group, which has, I'll call my group A, then I have generators G1 and relations R1, and I have another group, which may be B, presented similarly, then I can define the free product to be the group which has as its generators G1 and G2, and its relations R1 and R2. And so what this is saying is that if I just take strings, formal multiplication in my group, and if two elements that are side by side belong to the same group, then just treat them like they're in the same group. Just use the group multiplication from either A or B. But if they're not, they're from different guys, A and B, then I can't say anything about them. I can't commute them, I can't multiply them, I don't do anything, I just get a string of stuff side by side. Now, with this sort of nasty group in mind, let's think about what happens if I want to make the fiber coproduct. Almost said the fiber product. The fiber coproduct. Then what happens is I have my groups A and B mapping to A star B. And now I'm going to impose a thing C lying above. Then what happens is I need to impose some relations on this, which insists that the data from C, whatever it may be, is respected. So if I name these maps phi and psi, then what I want to do, that's not good, psi, there we go. Then what I want to do is take the group, which is built out of A star B, but quotients by the relation that imposes phi and psi have a common image. In other words, I force phi of G to be the same thing as psi of G. And this sort of construction should not at all be alien to those of you with a topology background, In fact, this is exactly the group that's constructed in the Van Kampen theorem, Seifert-Van Kampen theorem. And so the two examples that I just gave are actually related to one another via this theorem. So what the Van Kampen theorem says is if I go back to my picture over here, then I can split my surface into two pieces. And they have to be open pieces for the theorem to work, but it's okay. So maybe I divide this along this line, and I take a small thickening of it. And then I'll take a small thickening on the other side. And now I take the red piece to be everything on this side, and the green piece to be everything on this side. And of course, as you see, there's some overlap between the red and the green. Then what I've done here is I've written my space as a fibered coproduct of the two spaces with the red and the green discs. Then what the theorem says is that the fundamental group of the whole space, which is a fibered product, so maybe I write it as pi1 of u fiber product v over something, in this case it's the intersection, so I'll just write u intersect v, happens to be the same thing as pi1 of u free product pi1 v with amalgamation being taken with respect to the inclusion maps from u intersect v into u and u intersect v into v, respectively. And so, in other words, the Van Kampen theorem says that pi1 preserves fiber products. Well, in this version, I only did it for fiber products with two elements. You can make varying degrees of general statements for the Van Kampen theorem with more complex fiber coproducts if you like. But let's not worry about that. There's a lot that you can say that's very interesting about pi1 and homotopy limits and colimits, all of which is very interesting, but we'll deal with all of this when we've discussed things like derived categories in the distant future. For now, I just wanted to sort of draw this connection between these two examples, that I have this example on the level of spaces, and I have another example on the level of groups, and that I can make a correspondence between them via the fundamental group. Let's look at the dual notion now, which is the notion of a fiber product. And the fiber product will then be the projective limit of alpha. And we'll denote it by, I don't remember what I wrote the objects above. If they're called A, B, and C, then we'll denote this by A times B over C. And again, what is this like? Well, in the category of sets, we know that the product is the Cartesian product. So what does the diagram look like that we have? Well, now I've got something that looks like a product upstairs with things that are like projections. But there's a map, they have to have a common, these projections have to respect C. So in order to think about what this is like, let's think about other places where we have sort of products that are kind of messed up. A good example of this from topology is covering spaces, or if you know about fiber bundles, then you can think about those instead. What I'm going to say should work more or less exactly the same for those. So let's just think about covering spaces, because probably most of you guys know about covering spaces. I've been talking about pi1 a lot, so let's just stick to that. So let's think about covering, let's recall maybe at first that a covering map is a map which we'll just call pi from E to B, where I think of B as a sort of base space, E as a total space, and we have the property that for every x in B, there's a neighborhood U of x with pi inverse of U homeomorphic to a disjoint union of copies of U. So maybe I'll write this like this. For some number of copies I. And we say that in this situation that U is evenly covered. In other words, I'm thinking of this as I have like a point and I have a disk, and then sort of lying over this are stacked disks. They should all be the same size, but I'm a bad artist. And pi just sort of presses all of these disks down onto each other. Now, clearly, I could make a covering space in a stupid way by taking just a product of copies of x, like, or sorry, I guess if x is, or maybe b, I called it b. So I take any space b, and then I take some collection of copies of b, and I just form the ordinary product. That would be a covering space where the map pi would just be the projection onto the factor. But we can make more interesting examples of this sort of thing. Like, for example, on the circle, I can make a helix that wraps around like so. And topologically, that's just a line, right? This is just well, it is. It's a line that's been coiled, but topology doesn't care about that. And this can also be squished down onto the circle. And those of you who have seen this remember that what I'm doing here is I'm saying that the line is the universal cover of the circle, but if you don't know what that means, then don't worry about it. And of course there are other examples, like the sphere and the projective plane, and maybe those of you who know some physics know about SU2 covering SO3. S2, I should write these down, RP2, SU2 covering SO3. This example that I just drew here is R covering the circle. Okay, and all of these examples are very interesting. Hopefully you're familiar with at least a couple of them. And maybe even you know the story that such covering spaces are classified with what's called a Galois correspondence, which says that covering spaces that are connected, and you need some hypotheses like, semi-local, simple connected, blah, 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 some annoying technical conditions that we don't worry about, on correspondence with subgroups of the fundamental group. And if you don't know this, story, then go check out the great books by like Hatcher or Berdon. Hatcher's book is available for free on the internet, so just take a look at that. Anyway, let me get to what I wanted to say, which is that covering spaces can be sort of pulled back. I don't think I said this before, but fibered products are also called pullbacks. Maybe I should just make this really quick as a remark. Fibered coproducts, when you only have these examples where you have just 3 objects, fibered coproducts are often called pushouts. And fibered products are often called pullbacks. And if you've seen pullbacks like in maybe topology, like differential topology, like you've seen the pullback of a vector field or a differential form, then it's a fun little exercise for you to think about what that has to do with what I'm saying here. Maybe after this example, you're inspired and you can figure it out. So what I wanted to say is that covering spaces can be pulled back. So if I have the situation where I have the space B and I have a covering map, and then I have a continuous map, F from C to B, then I can form the pullback as a topological space, which will just be then E times C over B. And I obtain a map up here, which I'll call F prime, and a map here, which I'll call maybe pi prime. And this produces a covering space over C. And let me just try to sketch the proof for those of you maybe who haven't seen this. If U is evenly covered, let's say U is some open set. Let me not get ahead of myself. U is some open set, contains a point. U is evenly covered in B. Then this is, of course, done by pi, because we're living in B. Then I can look at this diagram, and what I see is that if I lift, first if I go backwards by F inverse of U, and then I lift by pi prime, realize that looks like prime minus 1 looks a little weird. I apologize. But this is the same thing as going the other way in the diagram, which is F prime inverse of pi inverse of U. And we know that pi evenly covers U, so that this is, in here, is some collection of copies of the inverse image, which maybe I'll call it, I don't know, V. So I'll call them VI. Then what I get here is some coproduct, some disjoint union basically, of F prime inverse of some copies of these V's. Now what we need to see is that each of these inverse images of the V's is mapped homeomorphically onto F inverse of U via this pi prime map over here. And in order to see that, what you do is you notice that the restriction of pi to each of the VI's to U along, that I can restrict each of these guys along F, and then I obtain a map F inverse U to U just by applying F, and I know that the restriction of pi is a homeomorphism. That's what it means to be evenly covered. And so, as a result, this just sort of follows automatically. And maybe what I'll do is I'll leave as a fun little exercise is to like draw some examples of this. Like, for example, how many sheets does the pullback of a cover have? If you don't know examples of covering spaces and you want to think about this exercise, well then obviously first you'll have to look at Hatcher or something to get a sense of what's going on. Okay, now let's do the thing that I promised that we would do at the beginning. We've only been here about 20 minutes. So let me show some theory that says why this story is sort of complete. In other words, why knowing just the story for co-kernels and coproducts tells us everything there is to know about inductive limits. And again, sort of analogously for projective limits. Of course, this is only morally true. Describing interesting examples can be, very involved and can be fun. But from a certain point of view, this will be everything. So now let's just consider the category of morphisms in I. We have two natural functors from I to itself. We have, and we call them source and target functors. And what these do is, given any functor, I should give them names, so I'll call them sigma and tau. What this does is if I have any morphism in this category of morphisms, which I'll call S from I to J, then sigma of S is I, and tau of S is J. So we have these two morphisms in the functor category. And then I can also take, for any functor alpha, I to some category C, then I can also construct some morphisms then here, one of which takes alpha I to alpha J, and the other just the identity map. So, and I have this, of course, this is alpha S, alpha I to alpha J. Sorry, I should be clear about that. So from this, what I deduce is that I have morphisms, which look like this. I can go from alpha of sigma S to the coproduct over all the alpha I. And then again, I have the identity map. And I can put these together to obtain a pair of morphisms where S is taken over all the morphisms here. Alpha sigma of S into this big coproduct, alpha of I. And let's say I take this pair of morphisms and I denote them by A and B, respectively. Then I claim that the limit, the inductive limit of the alphas, is the co-kernel of this pair. So in order to prove this, what we're going to do is we're going to work in the category of sets and then invoke unita. That's been our strategy for everything involving limits and colimits. So suppose I'm in the world of sets. Here, this is the definition of the inductive limit, so there isn't really too much going on. And so in particular, if I have any z, then I can look at lim alpha to z. And this is the co-kernel of the following. alpha sigma of S. Let's just make sure we get that right. Into alpha of I Z. And in this world, this is what I wanted to prove in the world of sets. And so now to conclude, apply Unita. So what we've shown then is that in an arbitrary category I, the inductive limit out of I is the same thing as a co-kernel of a morphism between two coproducts indexed by the objects and morphisms of I, respectively. In particular, the ability to form the inductive limit is then the same thing as the ability to form these particular coproducts and the co-kernel of the map between them. So we have as a sort of corollary of this, C admits small inductive limits if and only if it admits all small coproducts and for any pair of parallel arrows, their co-kernel exists. So I'll just say and has all co-kernels. Now, if you're only interested in finite limits, then you can maybe rephrase the theorem by insisting on just the pairwise coproducts, and then you can iterate this to get all the finite ones. But you have to toss in the empty coproduct, and you could probably make other levels of generalities by just sort of being careful about how you make the statement and just sort of staring at the proof, either as I've given it here or as Kashiwara and Shapiro do it. Hopefully I've been faithful to their argument. But the point is that you can make various statements about what types of limits you want based on insisting on which types of coproducts and which types of co-kernels you have in your category. And again, mutatis mutandis for projective limits and products and kernels, the story will be exactly the same. Okay, so I think this is a good place to stop. And next time we'll talk about one last interesting example that has applications and relevance to topology, geometry, algebra. It appears in a lot of places. And these will be called the direct and inverse limits. And I'm not going to talk probably a whole lot about them. The terminology is a little confusing. Like some people use these to mean a relatively broad class of things. Like they'll speak of directed and inverse systems that are like more general than the ones that I'm going to show. But this will deal with chains of morphisms. And the limits or co-limits, depending on which direction you go, that you can produce this way. And this will produce for us some interesting examples of objects in topology and geometry. And now in algebra. I think I'm going to talk about, the plan is to talk about solenoids as a certain kind of bundle. So I'll say some words about bundles and how you can produce these things just from looking at very simple dynamical systems, like on the circle. So maybe we'll think about dynamics and circle maps. And then I also want to talk about p-adic numbers. And of course, this is completion. A suitable kind of Cauchy completion. Well, I'm talking about p-adic rationals. I haven't decided if I'm going to talk about p-adic integers or rationals or what exactly I'll do, but something in this vein. Okay, so I think that's everything I wanted to say. And in that case, then I'll see you guys hopefully next week. Take it easy.